Hello students, in this video we are going to learn a topic which is called conductometric titrations, and before going to conductometric titrations I would like to give the factors which can affect the conductance of any solution. So this is the topic, introductory topic, which you must learn before learning conductometric titrations. So let us see. So throughout conductometric titrations, the most important thing is the word conductance. If I use the word conductance, that word indicates always specific conductance. Okay, so it's not equivalent conductance or observed conductance or molar conductance. It's always specific conductance. And for any solution, specific conductance of a solution, that is directly proportional to two factors. One is number of ions, the other one mobility of ions. Number of ions, indirectly you can consider that as the concentration of the solution. Mobility of the ions, that you can consider it like speed of the ions. So specific conductance depends on these two factors. Let us see some examples to understand how these factors are taken like criteria for telling the specific conductance value. Let us take some examples. See example 1 only. First see this. In the example 1, there are two solutions. Two solutions that are made up of same chemical, that is HCl, here also HCl. But what is the difference? Here the concentration of HCl is 1m, here concentration of HCl 2m. So obviously 2m HCl contains more number of the ions than 1m HCl. So you can say that this is the order of conductance. Which conductance it is? It is specific conductance. So this will show, second thing will show more conductance than the first beaker. That is the example. And let's take the second example. Example 2. In the example 2, when you observe it, both the solutions are made up of two different chemicals. Okay, one is HCl, another one is NaCl. But the common thing about them is both contain same concentration. That means both contain same number of the ions. For suppose HCl, if there are 100 HCl molecules in this solution, no doubt there are more number of molecules. For our explanation I am taking it like that. So if there are 100 HCl molecules, that HCl will be dissociated like 100 H plus and 100 Cl minus here. Here also if there are 100 NaCls, there will be 100 Na plus 100 Cl minus. So both the beakers contain same number of the ions. If both the beakers contain same number of the ions, okay, then you have to look into the second factor, mobility of the ion. Okay, so here there is a common ion between these two beakers, that is chloride ion. Here chloride ion is there, here chloride ion is there. So what is the other ion other than this anion? Here H plus, here Na plus. So chloride ion contribution for the conductance of the solution of both the beakers, that is same. If chloride ions are same, its contribution is same. So which ion is the deciding factor to tell the conductance of this solution? Cation in this case. So when you take this, here H plus, here Na plus, and the conductance of these two solutions, that is decided by mobility of these two ions. So mobility of these two ions. Okay, so mobility of these two ions, that means speed of these two ions. Which one is having more speed out of these two? H plus. Okay, mobility is greater than Na plus. Very important thing. What is the reason for that? Okay, Na plus, for Na plus ion, hydration takes place. Okay, surrounding to that. That is one reason. If hydration takes place, wherever Na plus wanted to go, it will go along with the hydrated layer. Okay, and H plus, when you just even compare the size of and H plus and Na plus, obviously H plus is smaller in size. Okay, so the smaller is the ion, the more will be the speed of that ion. But remember that whenever you are considering the mobility of the ion, always you need to consider the hydrated sphere of that ion. Okay, no doubt Na plus with the hydration only that will move. So here I wanted to tell H plus mobility is greater than Na plus. So based on that, out of these two solutions, HCl solution that will show more conductance than NaCl. Okay, so that is the point. Please remember this point, this will be coming one of our conductometric titrations. So if HCl concentration, NaCl both are same, conductance is high for HCl than NaCl. Okay, that is decided by mobility. H plus is having more mobility than Na plus. Hope you understood this example. Let me take further examples. So there are 4 examples here I am showing. Okay, in these 4 examples, let's see the example number 3 here. In this example, first beaker, second beaker, both the beakers contains acids, okay, and both the beakers contains acids of same concentration, 1m, 1m. But out of these 2 beakers, which beaker show more conductance? Obviously, first beaker greater conductance than second beaker. The reason is, this is the second beaker chemical is the weak acid, okay. The first beaker chemical is the strong acid. Strong acid dissociates almost 100%, so it will give more ions. Weak acids percentage of dissociation is very less, so that gives the less number of the ions. That's why this is like that. So based on number of ions, I can explain example 3. Now let's take example 4. In the example 4, NaOH, NH4OH, both are bases and both of them they have same concentration, but obviously when you just compare the nature of these two electrolytes, NaOH is strong base, ammonium hydroxide is weak base. Based on that condition, I can say that conductance of NaOH solution that is greater than NH4OH. Like that I can tell. Now take this 5th example. Acetic acid 1m, sodium acetate, okay, 1m. Out of these two, what do you think about a strong electrolyte? Acetic acid is the weak electrolyte than its corresponding salt, which is sodium acetate. So this is the strong electrolyte, okay, this is the weak electrolyte. Based on that, I can say this can give second beaker contains more conductance than the first beaker. That is depending upon the number of the ions. Always strong electrolytes produces more ions. That is the thing. Now take this example 6. In this example, ammonium hydroxide and ammonium acetate. Ammonium hydroxide weak electrolyte, but its salt is strong electrolyte. Strong electrolyte, here the word strong electrolyte, the meaning of the word is it is stronger than ammonium hydroxide. Okay, don't compare with another thing. So out of these two, obviously second beaker will show more conductance than the first beaker. So continuing our discussion, I am taking 4 more examples. With this I can conclude the 2 factors. So in the example number 7, see this, sodium hydroxide, sodium chloride. Out of these two, sodium ion is common in both the beakers, okay, and both the sodium hydroxide and NaCl, they are strong electrolytes, so number of ions are same. Now the conductance of the solution, that is decided by anion, here OH minus, here chloride ion. So please remember, OH minus speed is greater than Cl minus, okay. Mobility order, very important order. This will move with greater speed. So based on that, I can say that 1m NaOH that is having greater conductance than 1m NaCl. The reason is mobility of OH minus ions that is more than the mobility of chloride ions. Okay, that is the thing. Now example 8. So here silver nitrate, silver chloride. Out of these two, silver nitrate is soluble in water, silver chloride is insoluble, almost insoluble in water. So though there is a 1m AgCl in the solution, that is in the solid state only. So the one which is producing more ions is silver nitrate. So I can say that silver nitrate conductance is more than silver chloride conductance. Like that I can take. Now example 9. In this example, KCl, AgCl. As I explained in example 8, here example 9 also you can see that KCl is the soluble electrolyte in the water. AgCl, this is almost insoluble. If it is almost insoluble, how can it produce more ions? So obviously out of these two, KCl contains more conductance than AgCl. Now last example, barium chloride, barium sulfate, and hope some of you know already that barium chloride is soluble in water. Barium sulfate is insoluble in water. So based on this, I can tell that barium chloride, that is having more conductance than barium sulfate. So this is about factors. So there are only two factors. One is number of ions, the other one is mobility of the ion. So in the mobility, please remember OH minus speed is greater than Cl minus. At the same time, H plus speed is greater than Na plus. Okay. So let us go to the conductometric titration. This is the actual topic which you requested me to make one video. So let us take the definition of the conductometric titration. Okay, before going to the definition of conductometric titration, let's see what is a titration. In any titration, your aim should be to determine the quantity or to determine the amount of the substance present in a given substance. For suppose, if there is HCl in a conical flask, you don't know how much is the concentration of this HCl, you don't know it, but you know volume. Okay, so you are going to titrate with NaOH taken in a burette. Okay, so NaOH molarity you should know, and its volume that you are adding during titration also you should know. If you know M2 value, V2 value, and if you know the V1 value, okay, V1 is the volume of HCl that you are taking, M1 value, M1 is the molarity of HCl which is present in this conical flask, that you can measure it based on the equation, that is you know that famous equation M1 V1 by N1 is equal to M2 V2 by N2. Here N1 and N2, they represents number of moles of acid and base which are participating in the reaction according to the stoichiometry. Okay, according to stoichiometry N1 N2. So based on that you can find it. So how to find it? In normal titrations generally we are going to add one indicator. So wherever endpoint comes, indicator changes its color, and that can be the indication. Okay, you have to stop it. So that is the volume of the NaOH which is required to neutralize the HCl present in your conical flask. Based on that volume which you determined during the titration, you can find out the molarity of the HCl. So V2 value, that means volume of the NaOH that you are adding in normal titration. What is V2? V2 is the endpoint volume of NaOH. Okay, so that is decided by change in the color of your solution present in conical flask. That is the normal titration. Here there is no indicator in the conductometric titrations. Without indicator we are going to get it. So what is a conductometric titration? Let us see. The titration in which the determination of endpoint of titration is by means of conductance measurements. Okay, we are not going to see the color change. We are going to observe the conductance of the solution and we will measure that conductance throughout the titration. Okay, after measuring that values, based on that values, we will decide the endpoint. The purpose of any titration is to know the endpoint volume. So here that can be done by means of conductance measurement. Okay, so that is conductometric titration, basic definition. And as you know that all these titrations are based on the fact. What is the fact? Conductance of a solution at a given temperature, that depends on only two factors. One factor is number of ions present in the solution. Second factor is their mobility. Okay, so these 2 points whatever I have written, they are the basis for conductometric titrations. If you can read and understand them, these 2 points clearly, it is easy to understand, okay, the remaining part. Now let's take it. So in this video, I am going to give the graphs of all conductometric titrations. So that's why I wanted to take the types of conductometric titrations. Basically, in any chemistry lab, people will perform two types of conductometric titrations. One is acid-base titrations, second type is precipitation titrations. Within the acid-base itself, there are many categories like this. SA versus SB. What is the meaning of that? Strong acid versus strong base. Second one, B, weak acid versus strong base. Strong acid versus weak base. Weak acid versus weak base. And mixture of acids versus strong base. So 5 different titrations we need to study in this topic. All these they belongs to the category of acid base titrations. Okay. Precipitation titrations. There are 2 types generally. These 2 types only will be given in the exam. And the precipitation titration, in which one product of the titration is the precipitate. And the second type is 2 products of the titration are precipitates. What is meant by this? We will see with the examples. In the detailed explanation I will give it. So right now I wanted to show these are the different types of titrations that we can perform using conductometry. So let's take one by one. So first of all, I am taking the acid base titrations. In that I will explain in detail about strong acid versus strong base titration. Okay, so for this you must know how the experimental setup can be done, for which solution you are going to measure the conductance. If you have clear idea in your brain, you can easily understand what is happening inside that solution. So for that I am giving the experimental setup, okay, for the strong acid versus strong base titration. Let's see. You know the burette, and in the strong acid strong base titration generally burette is filled with NaOH. This is present in the burette. Okay, and there is a beaker. Inside the beaker we are taking hydrochloric acid. Okay, and one more point I wanted to highlight: in all our explanations of acid base titrations, we are going to take acid in the beaker, base can be taken in the burette. In the exam also, most of the times, 99.99% times, same type of the experimental setup will be given in the question. Always they will consider base in the burette and HCl in the beaker. Okay, once we have taken these two, shall we start conductometric titration? No, I said during conductometric titration endpoint, that is based on measurement of conductance values. So to measure the conductance values, we definitely need a device. That device is called conductivity meter. So nowadays conductivity meters are available for the low cost. So people are buying and they are doing this setup. So this is the just block diagram for the conductivity meter. Simply what is conductivity meter? There will be a block like this, and this is a meter actually, which contains a display. This display indicates the conductance of the solution. How it can indicate? Okay, so because this conductivity meter, this is connected through a wire to a cell. This cell is called conductivity cell. Those who completed the electrochemistry part, they definitely know what is conductivity cell. It contains 2 electrodes that are separated by a particular distance. Each electrode is having area of cross section. Okay, so these are the 2 electrodes. Okay, we have to dip it, then we have to connect it. Okay, and no doubt this is having another wire which we can plug into the socket. Okay, because we need power supply to run this meter. So now this is the experimental setup. Now what I am doing, I didn't add NaOH, just I fill the burette with NaOH and inside the beaker I have pure HCl. Okay, so how to do this titration? Simply from the burette I am going to add, okay, for suppose say first I will check the conductance of pure HCl. So here I am taking NaOH volume, okay, and conductance. Whoever performing conductometric titration, they will prepare this table. What is this table? Initially they don't add NaOH from the burette. They will check the conductance of pure HCl. They will get some value, say something like that, 1, okay. Then they will add 1 ml of the NaOH from the burette, okay. So here for example only I have taken conductance value 1, that need not be 1, that may be some value, say that is X, okay. And definitely after adding NaOH, some of the HCl is reacted. If HCl start reacting, then definitely there will be the change in the number of the ions, okay, and change in the nature of the ions, both are going to happen. So you are not going to get same conductance value after adding 1 ml NaOH, you will get some other value, okay. So say like, okay, instead of XY I am going to take X1, you are going to get X2, then add 1 more ml, then X3, then add 1 more ml from the burette, okay, then check the conductance of this solution, that is X4. Like that people keep on doing this up to certain volume, like for suppose say 50 ml, okay, they will do this and they will get the conductance values, okay. Those who will have the idea about graphs of the conductometric titration, they will definitely know that where to stop this, okay. It need not be always doing the titration up to 50 ml. You will come to know it, where should we stop it. But remember that throughout this titration, solution of your beaker will not change its color, okay, because you didn't add any indicator. But how can we get the endpoint in this titration? Okay, in the strong acid versus strong base titrations, once you have the data of volume of NaOH and conductance, you need to plot it. How to plot it? Take conductance values along y-axis. Okay, take volume of NaOH along x-axis. Okay, and I already told conductance means which conductance? Okay, specific conductance. So let us see what would be the shape of that graph. This is the shape of the graph. So here they plotted conductance along with volume of the base that they added. So initially when you see that, okay, this graph actually, when you observe the overall graph, what is the impression that you are getting? It is looking like a graph with two lines. In any conductometric titration graph, you can clearly track two lines. How to find out the endpoint, okay, of your graph? Simply both of these lines, okay, they are going to intersect at one point. That point indicates the endpoint. So that point means the corresponding volume. This is the endpoint volume of NaOH. Not only in this titration, in remaining types of titrations also, where two lines are intersecting, that point can be considered as the endpoint of conductometric titration. Now, as a curiosity thing, we must know why this graph it is having, okay, two lines like this. First line it is having the slope which is keep on first line it is in the first line conductance, what is happening throughout this first line, take it like first line and take it like second line. But during actual experiment, people, are they going to get lines? No. Or suppose at 0 ml they will get one value, at 1 ml they will get another value of conductance, at 2 ml, like that they keep on getting their values, okay. And after certain ml the values initially they keep on decreasing, after certain point the values keep on increasing. So once they get these values, they will try to join them, okay, and while joining them they know that the conductometric titration endpoint that is based on the intersection. So they will plot it like two lines, wherever they are bisecting or intersecting, that you can consider it like endpoint volume of NaOH. Now we must know why in the first line conductance is decreasing. To understand this, let us look into this equation. Inside the beaker, initially only HCl is there. Okay, nothing is there. Okay, but once you started adding NaOH from the burette, some of the HCl started reacting with NaOH to form NaCl and H2O. Okay, for suppose initially 100 H plus 100 Cl minus ions are there. Okay, you added just 1 ml of NaOH. Let us say that 1 ml. Okay, that 1 ml contains 5 Na plus 5 OH minus. Once you add them, okay, what will happen? The moment you add them, both of them, that means H plus and OH minus, they will react, they can form water. So after the reaction, for suppose initially Na plus 0, okay, Cl minus ions are also 0, H2O is also 0, okay, at time t is equal to 0. Once you add it, actually these reactions are very quick reactions. For my explanation only I am taking time t is equal to 0, time t is equal to t, but all these reactions are quick reactions. So once the time t is reached, okay, for my explanation instead of this, keep it like this. Okay, once the time t, that means reaction completed. How reaction completed? Out of 100 H plus, 5 already reacted. How many left? 95 H plus left. How many Cl minus reacted? Are they really reacted? No. Okay, so Cl minus ions will be in the ionic form only. How many Cl minus ions will be there? So you, for your convenient, you can write it like here 95 Cl minus ions, okay, and here 5 Cl minus ions. You can write it like that, but wherever maybe the Cl minus ions, the nature won't change. Okay, they are always Cl minus. But Na plus ions, 5 of them, they, for suppose if they reacted and they form NaCl, means in the NaCl also individual ions that are going to exist, Na plus and 5 Cl minus ions. And here OH minus ions, they cannot exist. Okay, clearly I am writing 100 H plus, 100 Cl minus, 5 Na plus, 5 OH minus. They are participating in reaction. Before doing reaction, 0 Na plus, 0 Cl minus, okay, 0 H2O. For our convenient I am telling that. Okay, so once the reaction is over, 5 H plus they are reacted. Okay, because of 5 H plus they are reacting with 5 OH minus, 5 H2O will be formed. Okay, now 95 Cl minus ions. Okay, and what are the remaining ions? Na plus this side, that is reacted, same Na plus that are just, okay, for our convenient we are writing it, they reacted, but they actually no reaction, only H plus OH minus only reacted. So this is the thing that is happening during the titration. Okay, but when you see the number of ions during the course of entire strong acid strong base titration, are they really changing? No, not at all. See, at time t is equal to 0, 100 H plus, 100 Cl minus, these are the ions. Okay, and just you added it, you added just these two ions before adding 100 H plus, 100 Cl minus. Once you add these two ions from the burette, 95 H plus, 5 Na plus, 95 Cl minus, here 5 Cl minus. Simply what is happening? Total cations are 95 H plus 5 Na plus. Okay, this is there. And what are the anions? 100 Cl minus ions, all as it is that are there. So what happened within this shortest time? 100 H plus ions, out of the 100 H plus ions, 5 of them they are replaced by Na plus ions. So let us assume this situation in the beaker. Okay, if the beaker contains 100 H plus ions, okay, another beaker contains 95 H plus and 5 Na plus. What do you think about the conductance of these two beakers? In the first beaker, all the ions are the ions of with high mobility, which are H plus ions. In the second beaker, all the ions they are not having same mobility. 95 H plus ions they are having high speed, 5 Na plus ions they are having low speed. This is the situation which will happen throughout the first line in our titration. Okay, throughout the first line what is happening, fast moving or high mobile H plus ions are replaced by slow moving Na plus ions. That's why conductance decreases. Very important point. I am repeating the point. So why the graph is decreasing, okay, conductance in the first line? Okay, the simple reason is high mobile H plus ions are replaced by low mobile Na plus ions. So once the endpoint is reached, what is the actually endpoint? All H plus is neutralized by OH minus. That means at the endpoint T is equal to T endpoint time. So what will happen? There will be no H plus, everything is neutralized. Okay, so Cl minus ions there will be there as it is 100 Cl minus. NaOH, definitely to neutralize 100 H plus you should add 100 NaOH. So 100 Na plus will be there. Okay, along with it how many moles of water will form here? Okay, that is the important thing. 100 moles of water that will form. So at the end point, so this is 0 H plus. At the end point, conductance of the solution that is due to only NaCl. Okay, so this point it is having some conductance value, right? Okay, that endpoint conductance is due to NaCl present in the solution. Okay, there is no H plus, there is no OH minus. But after the endpoint, when you see the graph, this graph is increasing the conductance. What is the reason for that? Because you don't know where is the endpoint. You keep on adding the NaOH from the burette. After the endpoint, there is no H plus, but once you add NaOH from the burette, which ions are adding? OH minus ions are adding. Let us say 5 OH minus 5 NaOH you added after the endpoint. Okay, 5 NaOH you added means already beaker contains 100 Cl minus 100 Na plus. You added 5 NaOH means 105 Na plus. Okay, this 5 OH minus. Okay, and obviously there is no reaction means already formed water, that amount won't change. So here what I wanted to tell, after the endpoint you can track OH minus ions in the solution. That number of OH minus ions, once the reaction is over, once the endpoint is over, when you keep on adding alkali from the burette, OH minus ions are keep on increasing. And you know that OH minus ions they have more mobility than Na plus ions. That's why I can say that increase in the conductance after the endpoint, that is due to increase in the number of OH minus ions. Very important point. Okay, so that is not due to increase in the number of Na plus. Though the Na plus ions are increasing, but the contribution of Na plus ions very less. Okay, that is the point I wanted to tell. So 2 points why this line is having decrease in the conductance. First line, the simple explanation is fast moving H plus ions are replaced by Na plus ions during the titration. And why second line is having increasing in the conductance? Simply number of OH minus ions increases after the endpoint. Why at the endpoint you can see some conductance? Why don't the conductance at the endpoint is 0? The reason is at the endpoint solution contains salt. That salt is NaCl. Definitely NaCl contains sodium and chloride ions. That is the reason for the conductance value at the endpoint. This is about strong acid, strong base titration. This is the graph for that. I hope it is clear. Let us take the next type of titration. Weak acid versus strong base. To explain this, I am taking strong base NaOH in the burette. Weak acid I am taking acetic acid. Okay. So which solution conductance you are measuring during the titration? The solution which is present in the beaker. For that only you are doing the measurement. Now see that this is the weak acid. Okay, this is the strong base. Both of them they are reacting. What is forming here? CH3CO minus, some mistake is there, I will change it, Na plus, sodium acetate will form. Okay, sodium acetate when compared to acetic acid, this is the strong electrolyte, no doubt. Okay, it's not weak electrolyte. So now let us see. Initially pure acetic acid is there, definitely conductance will be low. Okay, acetic acid is weak electrolyte. Okay, but during the titration I will come to this slight decrease. Let us consider the remaining part. Conductance is increasing till the end point. Later that also increase will be there. That increase is not taking the same slope, that increase is taking the another slope. Here also two lines are intersecting, and the point of intersection that you can consider it like end point or equivalence point. Okay, why conductance is increasing before the end point? That is the question. Okay, because weak acid, once it started reacting with NaOH, okay, once reaction is over, there is no NaOH with the weak acid before the end point. Okay, all the weak acid that is converted into strong electrolyte, which is sodium acetate. So till the end point, sodium acetate concentration keep on increasing. That's why conductance keep on increasing. Okay, once the endpoint is reached, again conductance, why it is increasing? The reason is, once the endpoint is reached, there is no more sodium acetate forms. Whatever NaOH you keep on adding, that NaOH will be there like NaOH only. Between NaOH and sodium acetate, which one is stronger electrolyte? NaOH is stronger electrolyte. That's why you can see more increasing the conductance after the endpoint. The line will be like this after the endpoint. Okay, let me erase these things. So I will draw it perfectly. After the end point, the increase in the conductance will be more rapid, okay, than before end point, because NaOH is stronger electrolyte than sodium acetate. And before end point, why there is the increase in the conductance? The reason is sodium acetate keep on forming, which is stronger electrolyte than acetic acid. Okay, this keep on forming. But what is this small area where conductance is first decreasing, then that started increasing? What is that small area? What is the reason for that? The reason is simple. Initially acetic acid is there in your beaker. Okay, once you treat this entire acetic acid with little bit of NaOH, what will happen? Little bit of CH3COO forms, sodium acetate forms. These two will be coexisting in the beaker at a time. Okay, at the initial level of your titration, these two, okay, they have one effect. That effect is common ion effect. Sodium acetate, because this is the strong electrolyte, acetic acid is the weak electrolyte. Because of formation of the little bit of sodium acetate initially, this suppresses the dissociation of acetic acid. What is mean by that? Whatever conductance it actually wanted to show, that also will be decreased because of common ion effect. Okay, because acetic acid can exist in the solution in the equilibrium, CH3COO minus Na plus, and this sodium acetate CH3COO Na, this cannot exist in equilibrium. Simply it will dissociate. CH3COO minus, this is Na plus. For the acetic acid, okay, this is H plus. So there is a common ion effect. Because of that common ion effect, dissociation of acetic acid initially, that is suppressed. If that is suppressed, the number of ions present in the original acid, that actually decreases. But once the enough concentration of sodium acetate started forming, then the increase will be as usual, that keep on increasing. Okay, this is the reason for that. Okay, like that you can take it. That's about weak acid versus strong base. Conductometric titration, wherever these lines are bisecting or intersecting, that is the end point. Now take the next thing. Strong acid versus weak base. Strong acid, that I am taking HCl, weak base is NH4OH. Okay, which solution conductance you are measuring? Conductance of the solution present in the beaker. Okay, so what is happening in between these two? This is the strong acid, this is the weak base. Okay, and what is forming here? This is strong electrolyte only, ammonium chloride. Okay, that is there. And what is there? Water molecules are forming. Let's see how the graph will be. Two lines are there, first line, second line. Where is the end point in this graph? Wherever two lines are bisecting, you can say intersecting, that is the endpoint. Okay, so when you see this graph, first line, why it is decreasing its slope, or why there is a decrease in the conductance till the endpoint? The reason is simple. Initially strong acid is there, okay, HCl, okay, chloride ions that are as usual, okay, high mobile H plus ions are replaced by low mobile NH4 plus ions during the titration. Number of H plus ions are decreasing, number of NH4 plus ions are increasing till the endpoint. That's why conductance decreases. Once the endpoint is reached, okay, you keep on adding NH4OH. If you keep on adding NH4OH, there is no appreciable increase in the conductance. Second line, it is almost looking like parallel to x-axis. That means volume of NH4OH axis. Why is it going to happen? Simply look into that. It is the weak base, right? Weak base, it is having very less dissociation. Though you add 2 ml, 3 ml, 4 ml, 5 ml like that, nothing will happen. That dissociation, that is just 1% or less than 1% dissociation, that cannot give significant change in the conductance. That's why after the endpoint, conductance is almost constant. This is the reason for that. Now take the next one, weak acid versus weak base titration. Okay, so weak acid, which weak acid I am taking? Acetic acid. Which weak base I am taking? Ammonium hydroxide. So when you do the titration of these two, which solution conductance you are measuring? Conductance of this solution. So this is the weak acid, this is the weak base, but the salt that is formed is strong electrolyte. Okay, what is happening during the titration? Definitely two lines will be there. When you see this red color line, is this line, is it similar to the line which you have seen in the titration of weak acid versus strong base? Let me take that. See this line, okay, this line and the line that you are seeing right now, both of them, they are same. So what is happening during the titration? So weak acid, that slowly reacting, that is forming strong electrolyte, that's why conductance is increasing. Why there is initial decrease? That is due to the suppression of dissociation of weak acid due to the common ion effect between acetic acid and ammonium acetate. And when you see the graph after the endpoint, where is the endpoint in this graph? This is the endpoint. After the endpoint, conductance is almost constant. Why is it happening like that? Is this line, is it similar to the line which we discussed in this graph? Conductance second line, it is almost having constant conductance. The reason is same reason, because after the endpoint only ammonium hydroxide you keep on adding, that cannot give appreciable change in the conductance value. That's why it will be like that only. Okay, so you can take it like that. Now we'll go for the next thing. This is very interesting case, mixture of acids versus strong base. And for the explanation, I am taking mixture of acids HCl acetic acid, and I am assuming that both the acids are existing at the same time in the same beaker. Now I wanted to study conductance of this solution while adding NaOH from the burette. If I do like that, okay, just take a general guess. Okay, so before going for that explanation, let me change, this is Na plus. Okay, just take a general guess. If HCl and acetic acid, both of them in the same beaker, if you start adding NaOH, which reacts first with NaOH? Answer is simple, always stronger electrolyte will react first. So HCl react first. Once HCl entirely over, then acetic acid reacts. So in this graph, if they are mixture of acids, you are going to get, okay, two endpoints in the same graph. One endpoint is for HCl complete neutralization, another endpoint is for acetic acid complete neutralization. So this graph, this is the graph. This graph, it is the combination of two graphs. What are the two graphs? Okay, strong acid versus strong base titration, please refer the graph. Okay, and weak acid versus strong base. Both graphs, when you combine that, you are going to get it. Okay, in this graph, why conductance is decreasing initially till the point A? The reason is HCl, that is replaced with NaCl. H plus ions are replaced with Na plus. That's why that is decreasing. After the first endpoint, why it is started increasing? Once first endpoint is over, X is the first endpoint. What is that? What is X? Volume of NaOH required to neutralize what? To neutralize HCl, only HCl. That is the value of X. Okay, once this is over, then which start reacting? Okay, acetic acid starts reacting. Once acetic acid start reacting, that means weak acid, acetic acid, that is replaced by sodium acetate, which is strong electrolyte. Then conductance is increasing. Okay, point A to B, the increase in the conductance is due to increase in the concentration of sodium acetate in the solution. Once point B is reached, this is the second endpoint, which you can say that this is the point where both acids are neutralized. Then from this graph, actually I want volume of the acid that is used for only the neutralization of acetic acid. How to calculate that? This is given by y minus x. Y minus x is volume of NaOH. Okay, which volume? Volume of NaOH required to neutralize acetic acid. That's volume. Okay, so please remember X is for HCl, Y minus X is for acetic acid. Once the acetic acid is neutralized, then graph again started increasing its conductance. That is due to increase in the number of OH minus ions, because you keep on adding OH minus ions. Okay, so this is due to decrease in H plus ions, and this is due to increase in concentration of sodium acetate CH3COONa, and this is due to increase in the number of OH minus ions. Okay, that's why that is happening like that. This is the titration of mixture of acids with strong base. By this we completed acid base conductometric titrations. Now let's take the last thing, that is precipitation titrations. Precipitation titrations. In that precipitation titrations, I said there are two types. Type 1 is the precipitation titration, in which one product is a precipitate. What is mean by that? See this example. KCl, this is electrolyte 1, and silver nitrate, that is electrolyte 2. Both of them, they are reacting. What is the thing that is forming? AgCl, this is product 1. KNO3, this is product 2. So two products are forming. One is only precipitate, second one is not a precipitate. In this case, how will the graph is going to look like? That we will see. And for that, we should take all my explanation. This is done based on this condition. Silver nitrate is taken in the burette, KCl, that is taken in the beaker, and conductance of the solution, KCl solution, we are measuring. Initially KCl is there. You started adding silver nitrate from the burette. Then what will happen? See this. This is the graph. This is the end point of the graph. You started adding. Conductance is not at all changing. It is almost looking like parallel to x-axis. Once the end point is reached, okay, then it started increasing. Why there is no appreciable change in the conductance till the end point? Simple reason. KCl is there. KCl is replaced by KNO3. Whatever silver nitrate you are adding, that is reacting with KCl, chloride content is becoming like AgCl. AgCl is completely insoluble in water. It cannot increase conductance. Okay, that's why keep it aside. So whatever KCl is simply converting like KNO3. And potassium ions, remember, out of the cations and anions, which will have more ionic mobilities. Generally cations they have more speeds than the anions. Here both chloride ions and nitrate ions, both of them they have same mobility. If both of them they have same mobility, then if they are replacing with each other, can it change the conductance? No. Okay, number it is not changing, mobility is not changing, conductance will be almost same. But after the endpoint, conductance started increasing. What is the reason? Once the endpoint is over, already KNO3 enough KNO3 formed. Along with it, what are the other ions that you are adding? You are adding silver ions, you are adding nitrate ions. Both these ions will be there in the solution. That ions keep on increasing. This increase is due to increase in the concentration of AgNO3. Okay, that's why this is like that. This is the endpoint. Okay, this is about precipitation titration type 1. Type 2, let us see. Type 2 precipitation titration. What is this type 2? The precipitation titration in which both the products are precipitates. Best example is magnesium sulfate. This is salt 1. This you can say electrolyte 1. This is electrolyte 2. Both of them they are forming product 1, product 2. Both the products are precipitates. Then what will happen? Let us see. To explain that, barium hydroxide I am taking in the burette, magnesium sulfate I am taking in the beaker, and conductance of magnesium sulfate solution I am measuring. And I did the experiment, I plotted this graph. Okay, in this graph, volume of barium hydroxide which you are adding from the burette, that is taken like this. Now let's see this. Okay, till the endpoint. Where is endpoint? Wherever two lines are intersecting, that is endpoint in any conductometric titration. That is the simple trick. So now take this. Till the endpoint, conductance is decreasing. Why till the endpoint conductance is decreasing? Initially magnesium sulfate is there, magnesium ions are there, and sulfate ions, both of them they have individual ions, ionic nature, they are existing, okay, freely. Once you started adding barium hydroxide from the burette, okay, some of the magnesium ions they are converted into precipitate, some of the sulfate ions they are converted into another precipitate. So number of magnesium ions, number of sulfate ions that are keep on decreasing till the endpoint. Okay, that's why conductance decreasing. After the endpoint, why is it increasing? Once the endpoint is over, okay, all the precipitates are already formed. Then whatever excess barium hydroxide that you are adding, that barium hydroxide that is soluble in water. Magnesium sulfate, barium hydroxide both are soluble in water. Only products are insoluble. So after the endpoint, when you keep on continuing the addition of barium hydroxide, then no precipitate forms, all barium ions amounts that increases, OH minus ions that also increases. So based on that, what can you tell? This keep on increasing. Okay, so that is going to happen like that. So that is the reason, okay, why it is increasing. So this is about the precipitation titrations. Okay, so for your okay remembering, I am giving one note. Okay, that note is mobility of ions. Which ions I am comparing? H plus ion mobility, OH minus ion mobility, chloride ion mobility, and Na plus mobility. The mobilities are in this order: H plus greater than, OH minus greater than, Cl minus greater than, Na plus. Very important data. So related to conductometric titrations. This is very interesting point. You can remember. So this is about that conductometric titrations. As a extra thing, this additional topic I wanted to give. What is that? What are the advantages of conductometric titrations? 5 advantages are there. One is colored solutions can be titrated easily without difficulty during the measurement of endpoint. In normal titration where you add some indicator, okay, for suppose indicator is phenolphthalein indicator, okay, it gives generally pink color in the basic medium. Okay, the solution whatever you are taking, that itself is pink color. Okay, then you cannot say that pink color you are getting after adding phenolphthalein endpoint is due to phenolphthalein or the solution. You cannot say that. So that's why colored solutions, normal titrations, indicator titrations you cannot perform. Conductometric titrations easily you can perform. Next, second thing, the equivalence point is accurate when compared to normal titration. Normal titration you cannot get accurate endpoint. This titration will get accurately. Accuracy is the second advantage. And third advantage, you know that no need of indicator. You already having conductivity meter. Next, fourth one, titration of weak acid, weak base can be performed successfully. In acid base titrations, for one titration you have no indicator choice. That titration is weak acid, weak base titration. There is no suitable indicator in normal titration, but you can do it with conductometry. And fifth one, titration of mixture of acids which contains two acids. This also successfully you can perform using conductometric titration. So these are the advantages of that. So this is all about conductometric titration. So please remember all the points that I have given to you. Just go through this video. Still, if you have any doubts, okay, please try to reach me. Don't hesitate. So this is about that. Thank you.